This video we're going to talk about pouring out a portion of solution from the stock. You can't find these sections in the textbook. However, this is a very important skills. Okay, so what means by pouring a portion out from the stock? Okay, stock. Okay, we just define as some large volume of solutions. So say for example right here. Okay, if you got a Coke. Okay, the Coke, say for example, we have 400 cm cube right there, and I see that, okay, oh, the sweetness of this Coke is perfect. Okay, it's very nice. Okay, I'm going to share with you. So what I'm going to do, okay, I'm going to pour 1/4 of it out from it. That means 100 cm cube. So when I got another beaker, okay, this time, okay, I'm not pouring all to you. Okay, I'm just pouring 100 cm cube to you. So you should find it, okay, the taste of the original Coca-Cola and also the 100 cm cube that I pour out for you, the taste should be the same. The sweetness, the sourness, okay, all these things, okay, should be the same. So you find that the sweetness is the same. That means that, okay, in the process, the molarity before should be equals to the molarity after. So in this case, okay, we find that 400 cm cube, if we have 8 particles in it, if I just pour out 100 cm cube out from it, that means I'm going to get 1/4, okay, 1/4 out from it, okay. So 400 cm cube, I just get 1/4. So you can see that, okay, we will have 2 particles in it, okay. So if we do the math, okay, if we want to try to find out the molarity of this solution, molarity should be number of mole over volume. Okay, so right here we have 8 particles, okay, and then volume will be 400 over 1000. Okay, so actually it's impossible, okay, but anyway, okay, it will be around 20 molar. Okay, so quite a lot. But in this case, okay, we'll do the same. Okay, we have number of mole equals to 2 particles there, and then we have 0.1 volume. Again, you have 20 molar. So you'll find that before and after, the molarity of it, okay, the molarity of the solutions before and after should be equals to each other. But the number of particles will severely drop. Okay, this one is a very important concept. Okay, molarity the same. Right now, molarity before and after, they should be the same, but the number of particles, okay, should reduce. Okay, if you just get a portion out from it. So how you see in the question, okay, for this kind of thing happen in the questions. So you can have a look right here. Okay, I'll just give you some examples. So the first one, you can see that 1.14 gram sample of water-soluble metal carbonate was dissolved in distilled water and made up to 100 cm cube solution. That means right here we got 100 cm cube solution, and then I have put 1.14 gram sodium carbonate in it. Metal carbonate in it, and then the most important part right here. Okay, 100 make up to 100 cm cube, and then 10 cm cube of these solutions required 25.3 hydrochloric acid for neutralization. That means, okay, this 100 cm cube, okay, we have taken out 10 cm cube only, and we have put it in the conical flask and do the titration. So you can imagine, okay, only 10 cm cube out of 100 cm cube, the number of particles must reduce, okay, must drop. If this particle drop, okay, the number of titrant add into it, okay, should also drop. If I'm not using 10 cm cube, I'm using this 100 cm cube to do the titration, I must use more titrants to do it. Get it? Because 100 cm cube, you got more number of particles, so you need more titrant to complete neutralize this one. So this time I just take 10 cm cube out, so therefore I will use less titrant, and I can use these stock solutions to do more trials, to perform more trials to get an average, so therefore we can get a more accurate results. So that's why normally, okay, when we're doing these titrations, we have a stock solution, and then we'll take out a portion of it to have the titration. Okay, so we have to see the difference in the number of mole in these two solutions. That is very important to identify this well. Okay, every time we'll say it like this: number of mole, the first one in 100 cm cube, it will be number of mole of M2CO3 in 100 cm cube. I will write it very clearly, top out like this. And then, okay, the second one, it only 10 cm cube, I will write like this way. Okay, so I will do the math. Okay, so in 100 cm cube, that will be 1.14 over, okay, m times 2 plus 12 plus 16 times 3, that is number of mole. Okay, but in 10 cm cube, say for example this is A. Okay, so after you got this number of mole, okay, how will be the amount, okay, in 10 cm cube? Basically, okay, very easy, you just divide this number of particles, okay, by this volume. Okay, you just break them down in unit volume. Okay, so this one is 100 cm cube. 1 cm cube, how much number of particles would that be? Basically, you divide this one by 100 first. Okay, but now this time, okay, not 1 cm cube, this is 10, so I just have to times 10. Okay, that will be the number of mole of particle in this 10 cm cube. Okay, so same thing happened, okay, in the other questions. Okay, I show you a few, okay, so you can get a sense. So we got 2 grams dissolved in water to make up 250, and this time 25 of these solutions required. This solution means this 250. So this time, okay, we'll make up a 250 first, okay, and then I take out 25, okay, for titration. Okay, so basically you have 2 grams, okay, 2 grams divided by the HX, that will be in 250. So if you want to find the number of mole of H2X in 25 cm cube, basically, okay, if this one is called B, okay, B, you divide it by 250, you find a unit volume, how much number of mole, number of particles there, and you times 25. Okay, so you do that this way. So last one, okay, more or less the same. You got unknown metal carbonate dissolved in water, make up 250, and 25 of this solution. So again, okay, you have to use that one divided by 250 times 25. Okay, so just give you one example. So, okay, I'll do fully for this. Okay, so in experiments, okay, we are having ethanol acid, and then 10 cm cube of the vinegar was first diluted to 250 cm cube. So you got a stock solution of 250 here, and then 25 of it, that means you take out 25, okay, and then require 0.5 m NaOH to do. Wow, you say so complicated. Okay, so no worry. Okay, first of all, you write down first equation all the time. Write down the equation. So this one should be 1:1 because OHH, okay, it should be monobasic, okay, 1:1, okay. You're not necessary to write the full equations, okay, but just for your own learning, okay, I write this one for you. So second one will be the data. The data tell you that, okay, we got 10 cm cube, okay, and then you dilute it to 250 cm cube, and then you get 25 cm cube. Basically, okay, I will write like this way, okay. I use an arrow to indicate the changes in it, okay. And then next, okay, you are going to this 25 cm cube. Okay, we have 3 boxes here. Okay, so 25 cm cube. Okay, we required 0.05 m NaOH to titrate it, and the endpoint will be 23.5. Remember, this amount of NaOH and also this volume is used to titrate this 25 cm cube CH3COH, but not this one or this one, because the number of mole in it will be different, okay, from here. So therefore, you have to align the boxes like this. I would say this one a L shape. So you have 0.05 m, and then you have like 0.0235 dm cube, okay, to do the titration. So this one is titrating against 25 cm cube. So therefore, I put it, align it in the same level. Okay, so what we are doing right now, okay, so of course there are many steps. Say what apparatus to deliver 10 cm cube. Of course, you're going to use pipettes, okay, However, it is wrong because you have to say 10 cm cube pipette. Okay, so 10 cm cube pipette. Second one, what purpose of diluting the vinegar before titration? Why we have to dilute it? Okay, again, like what we've said, if you didn't dilute the vinegar, the concentration will be very high. Then you need a load or a large amount of sodium hydroxide to titrate against it. Okay, so therefore what you're doing, okay, this is very important. Sometimes you may see this. Doing dilution is to save the amount of sodium hydroxide in the experiments, or use it in the experiments. Okay, so we can reduce the amount. Okay, if you don't know what I'm talking about, so you just imagine if I didn't dilute it, this one is a concentrated one. Okay, concentrated ethanoic. Of course, the NaOH you add in it must be much more, okay, than the diluted one. This one is diluted one. Is that right? So therefore, you can use less NaOH to do the titration. Then you can save money, save chemicals. Okay. So state a suitable indicator here. Okay, you got weak acid and strong base. Strong base. Okay, so the endpoint will be closer to, will be larger than pH 7. Larger than pH 7, better to use phenolphthalein for this. Okay, so now we come to calculate the molarity of ethanoic. We're going to find out the molarity in 10 cm cube. So we find the molarity here. Okay, so I do suggest all the times, okay, you do the conversions, okay, in terms of number of mole all the time. So what we are doing here is, okay, just based on this. Okay, so I think the questions you can do it later on. Okay, you can have that read that later on. So basically, okay, the first step, I'm going to find out the number of mole of NaOH because you can see the number of mole here, and then by mole ratio, I'm going to find out the number of mole of this one. Okay, and then I'm going to find out. So this one is 3. Step 3. Step 4, step 5, I'm going to find out the number of mole in 250 cm cube, and I'm going to find out the number of mole in 10 cm cube, and at that time, okay, I'm going to find the molarity. Okay, so have a look. 1, 2, we've done. 3, number of mole of NaOH, it will be M times V. Okay, M times V will be 0.05 times 0.0235. So here you will have 1.175 times 10 to negative 3. Wait, 0.4, okay, we're going to find the number of mole of ethanoic acid in 25 cm cube. Basically, this one is just mole ratio. So what you need to do is times 1 divided by 1 because ratio is 1 to 1, right? So it will be like this. Okay, remember write down the units. Get it? Oh, so next, okay, we're going to find out the number of mole of ethanoic acid in 250 cm cube. Remember, okay, in this process, we are taking out 25 cm cube in 250 cm cube. Okay, I am removing out from a 250 cm cube solution. So in this process, okay, the number of moles should reduce. If we get back from here to here, the number of moles should increase. Okay, so what we have to do is just basically like this. This is the number of mole in 25 cm cube, right? So what we do, okay, we just reverse the process. Divide 25, and this time we have 250. So you just multiply this one by 10, okay? So by doing so, you will have equals to 1.175 times 10 to the negative 2 mole, okay? So after that, okay, you're going to find, get it? Okay, so this one, okay, we'll just multiply this one by 10, okay, because from 25 to 250. So last one, okay, we're going to find the number of mole of NaOH in 10 cm cube. You have to know that, okay, this 10 cm cube, okay, are we going to divide it 250 and then times 10? No, because this is not extraction. Remember, this is a dilution process. The question telling you that, okay, you put 10 cm cube of ethanoic acid in it, and then you dilute to 250. You add water to 250. So the number of particles in the 10 cm cube, say for example, you add 2 particles in it, you add in this conical flask, actually during the dilution, the number of particles should be the same. So in this 250 cm cube, number of mole should be the same in this 10 cm cube. That's why you will find that this one should be exactly the same. Okay, I know that it will be a little bit confusing, okay, but you have to go through these videos one more time, okay, for these calculations, okay. So next, okay, that would be the molarity. Now we get to this part, okay, and then we can calculate the molarity here, because we finally know that original solution. In the original solution, we actually have this amount of number of particles. So number of particles will be like this, and then the volume, because molarity equals to number of mole over volume, right? So number of mole over volume, volume is 10 cm cube only, so therefore will be 0.01. So the answer for this one will be 1.175, okay, mole per dm cube. Okay, so in this part, okay, you should learn that, okay, how to draw a L-shaped things like that. Okay, the data, if you arrange them nicely, you know that which chemicals titrate with which chemicals, and then you can distinguish the process is removing a portion out from it or dilution in the process. In short, basically, if you have dilution, number of mole should be the same. If you have taking out a portion out from it, okay, a portion out from it, the number of mole should be increased or decreased in the process. If you just take out a portion, most of the time it should be decreased. But in this case, you see that we reverse. From 25, we think about the 250, okay, what is the original number of particle in 250? That in that case, that will be increasing. Okay, so this L shape is very important. Okay, in the process, we convert a number of mole, number of mole, number of mole, and number of mole. Finally, use the number of mole to find out the data that you want, the answer that you want. In this case, it's molarity. Then you convert the number of mole to molarities correspondingly. Okay, so in this videos, okay, we just learn how to calculate, okay, the number of particles, okay, number of mole of particles, okay, if you just pour a portion out from the solutions. Remember, in the process, okay, the concentration, if we have 4 particle, I take 1/4 out from it, okay, 1/4 out from it, okay, then I will chop it up, okay, I will have 1 particle here. In the process, molarity before should be equal to molarity after, okay. In the process, remember, number of particles, it should be reduced. Okay, so basically this is what we are doing, okay, in this video. Bye bye.